Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, now we prove the proposition which I stated last time, which characterizes perfect fields in terms of the irreducible polynomials being separable. So let us recall what we are proving. We are proving this proposition. Let K be a field then K is perfect if and only if every irreducible polynomial in Kx is separable. So proof: we may assume characteristic of the field is P positive, because if the field is characteristic 0, then we know every polynomial, every irreducible polynomial is separable over characteristic 0 field, because the derivative is non-zero and then the degree will be strictly smaller than f. Therefore, from there it is clear that irreducible polynomials are separable over characteristic 0 fields. Now, therefore, we assume characteristic P is positive. Now, we will first prove this implication, that we are assuming K is perfect and we want to show that every irreducible polynomial is separable. So, we are assuming K perfect, that means we are assume the Frobenius map which is from K to K is bijective. That is the definition we made, perfect definition. Field is perfect means this Frobenius map is bijective. Now, suppose we want to prove what? Every irreducible polynomial is separable. So, let f in Kx be irreducible. Suppose on the contrary we want to prove that this f is separable. So, suppose on the contrary that f is not separable, then we are looking for a contradiction. We are looking for a contradiction. So, we have seen if an irreducible polynomial is not separable, that is, it is inseparable, then we know f prime has to be 0. This is by earlier observation. The derivative is 0, and now we want to get a contradiction. Contradiction to what we will get? Contradiction to the fact that f is irreducible. So, f prime is 0, that will mean that f will be a polynomial. So, that will imply f is a polynomial in x power p, with g is a polynomial ai x power I is from 0 to d. This is in Kx. That means other powers which are the powers of x which are not multiples of p, they will be 0 because f prime is 0. Now, these ai's are coefficients in A. So, ai's belong to K, but K is the image of the Frobenius, because Frobenius is surjective. Therefore, each ai I will write it as sum pth power of some element bi. So I is from 0 to d, and bi are elements in K. So this is because the image is everybody. So Fp is surjective, therefore this. So therefore now look at these bi's and look at the polynomial h I am defining. This is the polynomial bi x power I. Look at this polynomial. This is a polynomial in Kx. Okay, and then what is f? Look at f. We want to check that f is not irreducible now. That will be the contradiction. F equal to g of x power p. That means in g I should put instead of x, x power p. So this is summation I equal to 0 to d, and this a is the bi power. So this is bi power p, and x I have replaced by x power p. So this is xpi, but now its characteristic p. Therefore this sum is same thing as I equal to 0 to d bi x power I, and then I have taken that p out of the sum. That is because p is the characteristic of the field. This equality follows from the fact that characteristic p is positive. This is when you expand by binomial, middle terms which are binomial coefficients, middle binomial coefficients, they are divisible by p, therefore they are 0 in K. That is why this equality. But what is this? This is h power p. This is precisely the definition of h. This is h power p, which contradicts the irreducibility of f. P is at least 2. So this f is not irreducible in Kx. Therefore, we have finished the proof of one implication. Conversely, we need to prove that if every polynomial is irreducible, then we want to prove that K is perfect. Conversely, assume that every irreducible polynomial in Kx is separable. And now to prove that Fp, the Frobenius map, is surjective. This is what we want to prove. Alright, so suppose it is not surjective. So suppose, then we should get a contradiction. Suppose, so the image of the Frobenius is Kp. So suppose I have an element A in K which is not in the image of Frobenius. Then I am looking for a contradiction. So now we have an element in the field which is not the pth power. So I look at the polynomial, I enlarge the field. So let L over K be a finite field extension. Which is obtained by adjoining pth root of A. So adjoining x with x power p equal to A. So that is what I am saying is, look at the field extension L. L is a simple extension generated over K by x and x power p equal to A. So this is a field extension, and this is a finite field extension. So what is the irreducible? So x belong to the 0 set of the polynomial x power p minus A. It's one zero of this polynomial. This is in L, that is x. So look at the polynomial, this polynomial we want to study, x power p minus a. This polynomial, when I write like this, x power p minus small x power p, I just a equal to x power p, this is x minus x power p. Therefore, see, therefore what we know from this equation, every factor of x power p minus a is of the form x minus x power r, where r is from 0 to p. Well, when r is equal to 0, this is just 1, this is a constant factor. So, we are not interested in that. So, this is not interesting for us. So, 1 to p. And therefore, what we know is every irreducible factor of this polynomial x power p minus a, this is a polynomial in kx, and I am considering irreducible factor also in kx, and it will be not r equal to 1. So, every irreducible factor has a multiple 0. In L. So, the same x will be multiple 0, because if you take irreducible factor of this polynomial, that first of all that is not x minus x, because that x minus x is not a polynomial in kx. So, since this polynomial x minus x, this is not in kx. So, all irreducible factors in kx, they will be higher powers of this. Therefore, they have multiple zeros. So, therefore, they are not separable. So, what we proved is, in particular, irreducible factors of x power p minus a in kx are not separable. This is a contradiction to our assumption. We are assuming that every irreducible polynomial in kx are separable, but here we produce irreducible polynomials in kx which are not separable. This is a contradiction. So, I remind you, we are assuming that every irreducible polynomial in kx is separable, but here we produce a irreducible polynomial which is a factor of this, could be this itself. This is a contradiction to assumption. So, this completes the characterization of perfect field. And now, I want to characterize separable field extensions. So, next is, we want to characterize finite separable field extensions. This is what we want to do. So, recall that when we say finite field extension is called separable if every polynomial, every element is separable. That means minimal polynomials are separable polynomials. But this is too much checking. So, I want to find an economical way to check that a given finite field extension is separable. possibly in terms of the degree of the field extensions. So, this is what I want to do it. So, first of all, note that let us do checking for simple extension. So, let L equal to kx over k be a simple extension. Then we want to, so x is separable over k, that is if and only if, this is a definition of separability of an element, mu x over k is a separable polynomial. That is if and only if the zero set of mu x in k bar, this cardinality equal to the degree of the mu x, as many as zeros, but this degree of mu x is equal to the degree of kx over k, that is L over k. So, an element, a generating element is a separable over k, that is if and only if the degree of the field extension is exactly equal to the number of zeros of the irreducible polynomial of x inside the algebraic closure of k. So, here k bar is an algebraic closure of k. So, this is one way to check the number of 0 equal to the degree of the polynomial. This is one possibility. So, I am going to enlarge on this, but before I do that, I want to note one observation. So, note that this is a remark. This separability of a field extension is a relative concept. What does that mean? That means it depends on the base field. So for example, suppose K is field of characteristic P positive, and we have taken an element A in K minus pth powers of K. This is the image of the Frobenius map. Suppose I have taken K, like we have taken in one of the proof, and suppose we have taken X is a 0 of x power p minus a. This 0 is in algebraic closure. So, K bar is algebraic closure of K. We choose an algebraic closure, we know it exists, and so this polynomial is a polynomial in K bar x, and therefore it has a 0, and so I choose that 0. Now, and look at the simple extension L equal to Kx. This Kx, this is a simple extension. Then we know L over K is not separable. Because we have seen that the minimal polynomial mu x over k has multiple zeros. This x is not in k, this x is not in k because it is not a pth root, A is not a pth root. But now, so therefore, this L over K is not a separable extension, or an element X. So, element X in L is not separable over K. But the element X in L is separable over L. Because what is the minimal polynomial of X over L? This is the simple X minus X polynomial only, because X is, so this is a polynomial in Lx, and this is a minimal polynomial of X over L, which has only the simple zeros. So therefore, element X is separable over L, but the same element X is not separable over K. So this concept separability of an element, it depends on the base field, it depends on the relative. So it's a relative notion. So this was the comment I wanted to make. All right. Now, to check the numerical criterion, I am looking for an easy checking condition which checks that this field extension is separable. So for that, I want to recall that. So in earlier lectures, we have considered embeddings, K embeddings. When we have a field extension L over K, finite field extension, and if you have any other extension E over K, and E is algebraically closed field extension. When I write like this, that means E is algebraically closed and it is an extension of K. I am not saying it's E over K is algebraic. Okay, so I will keep writing an algebraically closed field extension of K. That may not be algebraic closure. But definitely, if I look at K is here, E is here, and if I look at the relative algebraic closure, ALG, this is the set of all algebraic elements, all those X in E, such that X is algebraic over K, then this EALG is an algebraic closure of K inside in E. So this is easy to check. So easy to check. So what do you need to check? Let me spell out what do we need to check. First of all, because this extension is now algebraic, because I have taken only those elements which are algebraic over K. So this extension is algebraic. All that we need to check that this field, this is a field also we know. So this field is algebraically closed. That is what we need to check. And how does one check a field is algebraically closed? We take a polynomial with coefficients in that field and we want to check that it has a 0 inside this field. That is enough to check. Or in other words, we want to check that any irreducible polynomial here is linear. So if you take any element here, we need to check that this field is algebraically closed. That means you take a polynomial f and consider that as a polynomial with coefficients in E. So and E is algebraically closed, therefore definitely that polynomial has a 0 here. We want to prove that 0 is automatically here, but that will follow from the transitivity of algebraic elements. So which I will not write down the proof here. This is easy to check that this is one way to restrict it to algebraic closure of K. All right. So now what we want to do that? So we have considering the embeddings of K embeddings of L inside E. Remember, E is algebraically closed. So this set, I want to prove a theorem. This is a theorem I want to prove. This theorem has two parts. Part 1, the number of embeddings of L in E, this number is smaller or equal to the degree of L over K, and this is L over K finite extension and E over K algebraically closed field extension. This is part 1, and part 2 I want to show that this number of embeddings is independent of E over K. That means, that is, if E prime over K prime is another algebraically closed field extension, then these two numbers are equal. Number of K embeddings of L in E is same thing as number of K embeddings of L in E prime, and then that number is called the degree of separability of L over K if I prove this. So let us prove at least first part. So it's very easy, and proof what I will use is old long time back we have proved Dedekind-Artin lemma, and I will use that again here. So note that what are the embeddings? Embeddings of L in E, they are precisely the K algebra homomorphisms from L to E, and this is a subset of K linear maps from L to E, because K algebra means it's a ring homomorphism and K linear, and this is just K linear map. They need not respect the multiplication. So this is clearly subset here. And what does Dedekind-Artin say? Dedekind-Artin lemma that says that this set home K algebra of L in E, this set is linearly independent subset, linearly independent over K, over E, not over K, over E subset of the E vector space home KLE. This is a K, this is E vector, not only K vector space, this is E vector space. And what was the vector space multiplication? That is, if I have Z in E and a K linear map F, L to E, K linear, then how did we define Z times F? This on any X in L is defined Z times Fx for every X in L. This is Z is in E, Fx is in E, therefore this is defined with a multiplication in E. So these are linearly independent. In particular, the cardinality of this set will be less equal to dimension of this vector space. So in particular, cardinality of home K algebra LE, this cardinality will be less equal to dimension of E dimension of the vector space home K LE, and this is precisely the number of embeddings. And this, what is this dimension I want to compute? So let us compute this dimension. This is I claim that this dimension is precisely equal to the degree L over K. this equality follows from the following. So look at this vector space home, here K linear maps from L to E. But L is a finite extension, therefore L as a vector space is isomorphic to K power L degree of L over K, because this L is a vector space of this dimension. So therefore this is same thing as home K power L over K E. But this is isomorphic to, clearly this degree will come out. This is home K E power L over K degree. But this is isomorphic to E. So this is E power L over K. So it is a vector space E power. See, all these isomorphisms are isomorphism as, this is isomorphism as a K vector spaces. And this is isomorphism as a K vector space, and the last one is E isomorphism. Therefore, altogether this will be all E isomorphism. These are all E isomorphism, sorry, E. This is also E isomorphism. This is also E isomorphism. Therefore, this dimension equal to dimension of this, but which is clear that it is L over K. Therefore, we know this. So therefore, we proved the equality in inequality in 1, and I will indicate the inequality now 2. Remember, we want to prove that this is independent of E algebraically closed extension of K. So I want to prove that, so this is a proof of 2, the cardinality of embeddings of L in E or cardinality of the embeddings of L in some other algebraically closed extension. I want to prove these are equal. Okay, but that is also very simple, because now look at the embedding sigma L in E. So look at the image of sigma, that is sigma L. So L is isomorphic to sigma L, and this is contained in E. So I am going to replace, and this one we have EALG here. What is EALG? That is an algebraic closure of K in E. This is algebraic closure of K in E. We have considered it earlier also. Now, because L is finite, this is algebraic over K. The sigma L is an elements of E which are algebraic over K, because the elements of L are algebraic over K. This extension is algebraic. Therefore, this sigma L is actually contained here. Therefore, I am going to replace. So this is true for every sigma. So replace E by EALG and E prime by E prime ALG. The advantage is now these are algebraic closures of K. These are algebraic closures of K. And also the embeddings, the number of embeddings have not changed. And also note that embeddings, K embeddings of L in E and K embeddings of K embeddings of L in EALG. This is just a restriction. This sigma going to the restriction. No, this is the other way. So these are bijective. This is not change. Similarly, the other. So I can assume E. So we may assume, what is the advantage? We may assume therefore that E and E prime are two algebraic closures of K. But then we know by Steinitz theorem that there is an isomorphism. So therefore, by Steinitz theorem, E and E prime, they are isomorphic over K. That is, there exists a K isomorphism rho from E to E prime. This we know, rho. But then we can give a bijective map from embeddings of L in E to embeddings of L in E prime. This is just a map, any sigma here going to rho compose sigma. And obviously it is bijective because the other way map is, if you have tau here, that will be tau inverse, tau of rho inverse of tau. This is therefore bijective map, and therefore in particular their cardinalities are equal. That is what we wanted to prove. And note that this is isomorphism because because this E is here and EALG is here and L is here and K is here. So whether you take all embeddings of L in E, they will already factor through this because elements of L are algebraic, therefore elements of sigma L are also algebraic, therefore the images of sigma, they will factor through this. Therefore, we can identify elements of this as elements of this. So therefore, this is a bijective map. Therefore, we can replace E and E prime by the algebraic closures of K in them, and therefore by Steinitz theorem we know that E and E prime are isomorphic, and that isomorphism will give us a bijection here. So we have therefore proved completely that the number of embeddings is a good invariant of the finite field extension L over E. And now we will use this fact to prove that separable extensions have primitive elements. So that we will do it in the next lecture. Thank you very much.